Good afternoon, everyone. Welcome to our talk. We will be discussing the topic Achilles heel of JS engines, exploiting modern browser during WASM execution. First, let me introduce ourselves. We are a group of researchers interested in browser security, and we have found exploited multiple bugs in Chrome, Firefox, and Safari. Now, let's dive into the background of our research on this topic. This table shows the exploited V8 bugs in 2024. It's collected by Silo from Google. We can see that the WASM bugs are all introduced in the past year. Some of them do not even need to bypass the V8 sandbox protection. Since WebAssembly was introduced in 2008, there have been researchers into its security. All the vulnerabilities can be summarized into two types. One is compilation issues such as errors in bytecode parsing. The other is check missing in memory isolation, such as out-of-bounds access when expanding memory, accessing JavaScript objects mistakenly. As the researcher has progressed, the old attack surface has been reduced. In the past 2 years, new proposals like WASM garbage collection brought new changes to WASM. This development introduced new issues for WASM. JavaScript has more optimization than WASM does, and thus includes more security checks. WASM is a low-level language. It can operate stack and registers directly, and has fewer safety checks and vulnerability mitigations. In addition, there are more JS fathers than WASM does, so many JS bugs have been discovered by internal fathers. In last year's Black Hat Asia's conference, we discussed methods for finding issues in the WASM compiler of Safari. Errors in the compiler can lead to compilation failures, which we classify as compilation bugs. However, if the compiler generates incorrect code that can still execute, we classify this as execution issues. Execution vulnerabilities are generally more exploitable than compiler vulnerabilities. So how do we find new bugs from the old module? We will start by analyzing recent vulnerabilities to identify new attack surfaces in WASM. Here is a simple example of calling WASM from JavaScript. The WASM test code is represented as binary code, stored in a JavaScript array. When we call new WebAssembly module, it passes and compiles this binary code. In the execution phase, the WASM instance objects export WASM function and invoke it. Here is the overall architecture of the WASM virtual machine. The upper diagram means the compilation phase. It takes WASM binary code as its input and produces machine code or optimized code. The lower part represents the execution phase. It also uses on-stack replacement to dynamically replace code with optimized code when the code becomes hot. So what bugs may occur at execution stage? The execution phase can be divided into 3 sub-phases. We found that the code here is less tested, so we choose it as our new research target. Now we will have more detailed introduction about execution. The runtime build provides support for objects, memory, and stack frame switching for the execution of WASM, so that it can be executed in the independent memory. Bytecode execution refers to the compiled machine code and optimized code running in the virtual machine. The external interaction phase refers to the part where WASM interacts with other modules, such as JavaScript and WebIDLE. The runtime build phase involves three aspects. The WASM engine initialization provides a global environment. The runtime initialization sets up call information and call frames for specific WASM instances. The tear-up makes preparation for context switching when OSR occurs. Vulnerabilities in this phase are related to the design of the WASM runtime structure. Complex contexts may lack certain boundary checks. Here is the Chrome bug of .21 2024. There is a type array where the first meaning types are user-defined, followed by system default types. If checks are missing, users can define types out of this range, causing the runtime to treat user-defined types as system-defined. This bug can be transferred into type confusion. Similar issues have been observed in other browsers. For instance, in Safari, the stack overflow checks for WASM function is insufficient. When hitting WASM exceptions, the instance pointer is uninitialized. The bytecode execution phase takes the output from the compiler as its input. V8 has liftoff and turbofan. Liftoff is a baseline compiler. It generates machine code and executes it. During the execution, if a particular piece of code executes frequently, it is recompiled by the optimizing compiler turbofan, which generates optimized code that dynamically replaces the original code. In this part, we are concerned with the issues that can pass through the compilation phases and causes problems during execution. The new proposal will also introduce new operation codes, thus affecting the bytecode execution. After extensive vulnerability research and fuzzing, we found that vulnerabilities in this area are often related to newly introduced proposals or bytecodes. For example, these 4 vulnerabilities are all related to WebAssembly garbage collection, ultimately leading to RCE attack. As WASM evolves, its interaction with JavaScript has increased, such as state transition and object interaction. Based on whether they involve WASM bytecode, we can categorize these interactions into active and passive interactions. The active external interactions are explicit interactions generated by bytecode. The bytecode are designed to interact with the JavaScript, such as import, export, and callref. Through these bytecodes, JavaScript objects and functions can be imported into WebAssembly environment. Well, passive interactions do not involve explicit bytecode. Instead, they occur through some mechanisms and object interactions. So how do JavaScript and WebAssembly exchange data with each other? As we can see, the WASM and JavaScript use different type systems. For example, WASM uses types like I32 and struct_ref, while JavaScript uses types like SMI and JavaScript objects. So how do they pass variables to each other and communicate? For example, there may be 2 different results of adding the same number if they use different types, just as the following picture shows. To avoid this problem, compilers introduce glue code. This glue code converts variables between different types, enabling seamless interaction and function calls between the JavaScript and WASM. For example, in V8, there are 2 wrappers, WASM to JavaScript and JavaScript to WASM. These wrappers are used for converting functions and objects between the 2 languages. We can use these 2 wrappers to handle the conversion of parameter types according to their corresponding mapping, such as converting WASM I32 to SMI. The wrappers fill the call stack of the invoked function with the converted parameters. Once all preparations are complete, the execution jumps to the extra function start entry. So WASM code is optimized by the WASM compiler, and the JavaScript code is optimized by the JavaScript compiler. But what about the glue code between them? In fact, this glue code is in a state where neither of the optimizers fully manages it. Therefore, it can only be optimized in a relative isolation. Every function in WASM has a signature. The first issue of WASM to JavaScript interaction arises when analyzing the signature of an imported function. It lacks considering invalid signatures. This oversight can lead to incorrect parameter types being passed during execution, causing type confusion bugs. For the issue on the right, if there is a JS call to a WebAssembly function, and within that function, there is another JS function call, the problem arises when the JS to WebAssembly line retrieves an incorrect instance object type, leading to type confusion. Apart from active interactions such as JavaScript and WASM functions calling each other, there are also passive interactions. The proposal such as WASM exception handling weakens isolation protection of WASM memory. Old WebAssembly did not have exception handling, so some exceptions that could have been caught would directly stop program execution. The WASM exception handling proposal introduced the try catch mechanism in WASM. When an imported JavaScript function is called within a try block and throws an exception, the exception can be caught by the catch block in WASM. Similarly, exceptions thrown by WASM can also be caught by JavaScript catch blocks. If not implemented properly, these interactions can lead to side effect. Memory and table in the WebAssembly virtual machine serve as isolated memory for storing. However, in the design of JavaScript, they are fundamental JavaScript objects, typically implemented as array buffer. As a result, they retain some characteristics and attack surface of array buffer. Historically, many vulnerabilities have arisen due to side effects from the grow method used to expand the memory of WebAssembly, leading to use after free issue. Such vulnerabilities faded after 2017, but now they are coming back with the increasing interaction between the JavaScript and WebAssembly. The goal of WebAssembly garbage collection is to support high-level language by allowing the virtual machine's garbage collector to manage memory for programs running in the VM without needing to translate GC operation into WASM. The implementation of GC in the WASM VM requires the ability to provide non-linear data structures and reference external objects. This has introduced new objects like WASM array and WASM structure. So far, we haven't observed vulnerabilities directly tied to the garbage collection feature itself. The primary concerns have new structure objects that break certain security assumptions in it, leading to issues like multiple definition of the same property of the object. Based on our analysis of recent WASM vulnerabilities and our own findings, we have identified three main attack surfaces. First, new processes like exception handling enhance interactions between JavaScript and WebAssembly. Second, issues can arise from type translators between WASM and JavaScript, such as type conversion and call stack switching. Finally, the development of new optimizers may introduce new attack surfaces in the future. Okay, the remaining time will be taken over by my friend Long Cao.
Hello, everyone. Hi. Yeah. I think we already know the issues that need to be focused on, right? Many problems during the execution process are actually not sufficiently tested. Yeah. Especially due to the increased complexity in the execution phase of WebAssembly and interaction, which is caused by the new specifications introduction. At Black Hat Asia last year, we just discussed the WebAssembly generator, but using it directly to explore the new attack surface we are addressing in this talk is obviously not suitable. Of course, we should still review a little bit. We first need a WebAssembly generator to produce some semantically roughly correct WebAssembly samples. And next, the question arises. We need to test the factors that increase the complexity of the WASM. So the first step we take is to enrich the WebAssembly generator itself. Then, we made a small modification to the generator when producing WebAssembly samples, which was to increase the use of the import, right? The imports. After generating imports objects with V8 WebAssembly compiler further randomly, the subsequent work of the WebAssembly generator is to treat those import objects just as a local object in generating next opcode. After the entire WebAssembly modules were completed, we collect a list of the import and export we just used, and which we defined as a shared object list. So, the next step is to complete the shared object list, right? Which is achieved by writing a unit generator with fuzly, a powerful tool, right? And our approach is similar to a toy project named fuzly for WebAssembly. Meanwhile, another optimization on the fuzly side is to increase the usage frequency of WebAssembly objects and to mutate them. The overall idea of the mutation is to replace the object originally generated in the fuzly program with shared object we just introduced. This includes the equivalent replacement of import and export functions for original functions, as well as object replacement. Of course, we have also made 10 template additions. Yeah, the template is always good. We have also made template additions of the two WebAssembly generators, focusing on generating JIT mode, such as loops and inline, and considering that the exceptions, or WebAssembly exceptions, are currently a cross-language feature. So we have to create templated generators for exception generating across WebAssembly and JavaScript. This evolved template within WebAssembly regions that capture exceptions through by JavaScript, and templates within JavaScript that capture exceptions through by WebAssembly. Those templates use fixed function name during execution. Indeed, by the end of the phase, the generator part is essentially complete. But we still need to make some optimization to FL++. First, let's review the traditional form of the fuzzing loop used by previous WebAssembly compiler fathers. You can just see that all the bytes from FL++ can be fed into the WebAssembly generator, allowing it to continuously generate WebAssembly samples. However, for a system that includes two corresponding generators, that is WebAssembly generator and JavaScript generator, each part needs to independently consume the root bytes during operation. Therefore, we just split this random output from FL++ into two parts, feeding them separately to the WebAssembly generator and the JavaScript generator. Currently, we use a cutoff length of 1,000 bytes. It's mainly because if the byte count is too short, it just limits the effectiveness of the generators. Of course, this also requires the setting in the samples length argument of the FL++ itself. Okay. When we actually start fuzzing, we encounter a program. We just encountered a problem where the samples generated by the fuzzer would frequently trigger errors during the compilation phase, or in other words, fail to reach the execution phases, which is really contrary to our desires. In fact, there are many reasons for this. First, it's nearly impossible for the fuzzers to just completely bypass the checks during the compilation phases. However, when we just switch the target, the feature cannot always stay synchronized, leading to very frequent fails when very new features are tested on engines that do not support them. So we optimize the for loop. We just found that the error message can just show the engine's processing stage clearly. For instance, pass and compile error logs are pretty different from runtime error logs, and this is true for nearly all the engines. Based on the observation, we added a regular expression matching strategy to FR++ to determine the process phase based on the engine's output logs. Because please see the red lines. Samples that belong to the execution phase are most likely to be mutated, while those are not in the execution phase are directly removed from the queue. This strategy greatly increases the proportion of the samples in the corpus really trigger the execution phases. Our father has found over 10 bugs, and several of them are pretty easy to exploit during the execution process. Next, we will enter the exploitation part for several WebAssembly vulnerabilities. The first exploitation is for WebAssembly. The first exploitation is for Chromium. The background is WebAssembly and JavaScript interactions are supported by wrappers. V8 has a generic WebAssembly to JS wrappers for this. The implementation of the wrapper uses architecture-related built-ins and use lazy compilation, which means compilation is that only when the import JS function is called, and this is friendly for low-end devices. The bug was introduced in the patch that fixed another bug related to the feature named JS2 WebAssembly wrapper inline. Please note that this is a critical function check whether the WebAssembly to JS generic wrapper features was enabled. But however, in the subsequent logic, the part that actually emit the code that did the code that actually emit the wrapper code did not check this bug anymore, which breaks the assumption. And we also found that there is no check in the runtime about whether the signature is compatible across WebAssembly and JS. The code on the right side displays the basic functionality of the wrapper in the runtime. We would like to know a little bit more, just like how the wrapper converts variables. Actually, in WebAssembly stack, variables are three categories: that is GP, FP, and stack. WebAssembly to JS wrapper SM functions will set up the regions, and then WebAssembly to JS wrapper CSA will be responsible for generating specific JS object. The process mainly involves 5 steps to list, just as listed. The overall idea is to transfer the WebAssembly stack to a fixed array in JavaScript, with the most critical step being the second one, actually, taking out the parameters in order. However, in the getStackSlot function, we found that data copying is always done in byte of 804. Depending on the architecture, the length of the pointer, right? But what about the themed type? Themed value are stored as 16 bytes data and the stack, not in 8-byte unit. Therefore, when converting themed data, the translator performs getStackSlot, which first processes the lower 8 bytes of the themed value as the first variables, and continuously treat the upper 8 bytes as the next value. However, the signature at the time will just remain still, so thus will cause type confusion. Yeah. The confusion needs to be cast into JavaScript object, right? So there are 2 branches in V8. In the first branch, the lower 4 bytes can be cast into JavaScript object and returned as a parameter back into the import JavaScript functions. So we got a fake object primitive directly. In the second branch, the entire 8-byte data can be used as the parameters of WebAssembly generic WebAssembly to JavaScript object function. The function name is a little bit complex. To generate a new WebAssembly functions. This can break the V8 sandbox, but this is not the scope of our talk. Just like this. Okay, let's assess our situations. We can fake any address as a JS object and operate on it, but we lack a suitable fake location and address leaking primitive. We can resolve it using heap spring. First, we can count the memory of a high address by allocating a pretty large array buffers. And we can next fix several JavaScript string objects with very large lengths value on this array buffer. And next, we allocate object with marker in V8 heap. Please note that while non-readable and writable protected segments exist among different V8 heap sections, it's pretty easy to find stable mapped V8 heap addresses on the sufficient memory pressure. Next, we trick the bug, get the fake JS string handlers with these high addresses, and then use the slice method of the JS string with a fake, this is just a fake JS string, right? We can search the V8 heap memory to locate the JavaScript object containing markers, we just said. The final step is to transfer the fake object into the array buffer to achieve upstream address, read and write, and RCE, just as I do. The first step to show, this is a demo. Yeah. Okay. We open a browser and check the variant. And just visit the park. Yeah. Pop the calculator. Okay. And this is exploiting the Android platform. If we just consider 64-bit system, the situation is somewhat different. Notably, in V8's memory allocation, certain features can help us find fixed addresses, such as map and empty fixed array in same binary and hard-coded string on the same execution environment. We can use hard-coded string to get a stable fake object addresses, while the REST exploitation is just similar to the former ones. Okay, so now you have probably noticed something critical. The data from scene is usually as a fake object without any checks, right? Just very different from the strict checks in JavaScript. This also happens in other engines. Let's look at some exploitation examples in Firefox. The first vulnerability we will discuss is related to tail calls. Tail calls optimization saves stack space by reducing the color space. Just consider the normal color with tail calls as an example. And the bug is when SpiderMonkey recycled the stack frame, SpiderMonkey is the JavaScript engine of the Firefox. When SpiderMonkey recycled the stack frame, the frame pointer moves too far. It overwrites the locals of the parameter functions when copying the arguments of the children functions. So, how to exploit it? First, we use this bug to overwrite as an I32 array reference and to the position of the I64 array reference in the caller, allowing us to access the context beyond the I64, R62 array with a larger offset. We need to first explain why we're just doing this. Okay. The reason, actually, this is also relying on the issues of missing checks, missing really critical checks in SpiderMonkey, especially type checks. Let's look at the example code generated for accessing a WebAssembly array. The generated code first checking the memory address is within the range of the array length. If this is within the range, it just visits the opcode at 0x88. Yeah. The value is actually an offset calculated during the compilation phases and based on the type of link and is hard-coded in the generated SM code. So Was the type checked? No. Only the index was checked right. I know this wouldn't be the case in JavaScript because dynamic typing programs are filled with type conventions, so we need to check in JavaScript. However, it turned out that strongly typed languages like WASM also need some type checking to increase the difficulty of the exploitation. But unfortunately, they did not. Therefore, we used an I32 array to replace the larger one in order to out-of-bound read and write with a valid index. And by allocating the object which we want to leak, can the arrays in advance, the address of a primitive is completed. Just like this. With the leaked address, we can continue to forge WebAssembly array on array buffer by using the vulnerability to replace legal WebAssembly array with an int value, targeting fact WebAssembly array address, which every field under control arbitrary read and write can be easily achieved. Oh. Please note that we have to use some special structure to bypass the non-box strategy of SmartMonkey. Finally, the method to get shell is to change the git address of a function class to shellcode address, which can achieve through git spray using float.js array. And please note that the SmartMonkey stores all the floating point numbers together at the end of the code and access them via an index like RIP plus XS, blah, blah. So the shellcode does not require small jumps within the float point as usual, like number spray technology. And let's turn to the case 2. The root cause of the vulnerability is that this is the length variable intake overflow of a renew in the generated code. This allows inline field allocation, something like the inline object, with pretty large length. This is a typical out-of-bound bug that and it is very easy to exploit. You just might wonder if such a simple vulnerability still exists in 2024. Actually, this vulnerability is in the generated assembly code. And the assembly code checks if nursery allocate account, whatever, just a flag, is 0 and jump to out-of-line code if it is. Only after initial through out-of-line code to set a flag, then we can allow assembly code to execute it. Thus, to just trigger the vulnerability, and extra renew operations is required. We achieve out-of-bound read and write directly by making 2 new arrays and using a large length on the second array. Then combining WebAssembly object to transfer OMB primitive into an arbitrary read and write primitive. But in fact, we haven't performed the address leak, right? Here we can sweep the data field of the 2 different type WebAssembly array. In principle, this allows us to lead the ref into the form of R32 without any check. If we place the JS objects that need to be leaked in the ref array, then we can just read the value using the R32 format. So we achieve the address of operation. Then the git spray is same as before. Okay, so at this point, exploitation process is completed. Another thing I really want to discuss is that patch is a patch for the box, which just adds the checking to the value of the length. But please note that what we are curious about is that the original function of this part of the code is to avoid the allocation space being greater than the limit, right? We think that the check itself had nothing to do with the outer condition statement, that is the if condition, checking the non-element is constant variable. So there should be similar checks in the else branch of the outer if conditions just with the same logic. In fact, there is indeed the same checks in the WebAssembly new array object, like the red part, yellow part, sorry. But even include the same in integer overflow error. What a pity. So this leads to the next issue. This is the same integer overflow vulnerability. The difference is that the first one is targeting the WebAssembly new array object fixed function, whereas the second one is targeting WebAssembly new array object function, which can be directly invoked in baseline compiler. And the exploitation technique, the technique and the steps stay same. Okay. Here is a conclusion. Introducing the concept of WebAssembly execution vulnerabilities, and we just analyze the attack surface of those vulnerabilities. And we have improved and integrated WebAssembly and generated fuzzy testing framework and propose a targeted vulnerability finding method using multiple methods. And at last, we analyze high-risk WebAssembly execution vulnerabilities we found in mainstream process and show how to exploit them with less check than JavaScript ones. Okay, the talk is about over, and we really thanks to the collaborators for this talk. Thank you. So if you have any questions, please feel free to ask us in Twitter, and we are online and waiting for it. Thank you.